A few videos ago, we looked at constructing interpolating polynomials by using the Newton forward difference table. In this video, we will look at constructing interpolating polynomials using the Newton backward difference table. The data in this case are in this notation, xi, fi, that is the usual thing, but we are going to number the subscript I from 0 to minus n. So 0, minus 1, minus 2 till minus n. So you will have data points like x0 and the corresponding f value will be f0. Then you will have a data point which is denoted by the symbol x minus 1 and that corresponds to an f value which is indicated by the symbol f subscript minus 1 and so on. And in this particular example, we are going from 0 to minus 4. We have 5 data points. So 0 to minus 4 means you will have 5 data points. So the table is like this, and we arrange the data so that we have the data as increasing, right, from the lowest value to the highest value of x and the corresponding f of x values. And the base x value is the largest value. So whatever is the largest value at the bottom of this table arranged like this, we would call this as x naught. Now we can reach any x using this relationship. This is exactly what we did when we did the forward difference table as well. Here we are using x naught as the reference point or the base value. There we used something called x1 and we numbered the data differently, x1 to xm there. Here it is different. So kindly note, from the reference point, that aspect remains the same. From the reference point, you are going to jump alpha steps based on the step size of h. And we again assume here that h is constant. That means the gap between successive x values is the same. And when you have alpha is equal to 0, we will be at x naught, the base point. If alpha is minus 1, we would be at x is equal to x naught minus h. So that is x minus 1. And if you jump 2 steps, so if you look at x is equal to x naught minus 2h, we would be at x minus 2 and so on, right? So I hope this is also clear to us. And any value of x between x naught and x minus n, you can reach by using suitable alpha values. So if you want to reach a value of x is equal to 3.5, we know that alpha must be minus 2.5. Because alpha is equal to minus 1 will take us here, alpha is equal to minus 2 will take us here, and alpha is equal to minus 2.5 will take us to x is equal to 3.5. And here we will use e to the power of alpha f of x is equal to 1 minus the backward difference operator raised to the power of minus alpha f of x. Remember, we wrote two expressions for e. One expression was e is equal to 1 plus delta, the forward difference operator. Another expression for e was 1 minus the backward difference operator inverse. So when we use the Newton forward difference table, we did e to the power of alpha and we said that is going to be equal to 1 plus delta to the power of alpha. And then we did the binomial expansion of this right hand side and got that expression involving powers of alpha. Here, if e is this, e to the power of alpha will be 1 minus the backward difference operator to the power of minus alpha. And you apply f of x to both sides, you get this. So there is a lot of parallel between what we did earlier and what we are describing now. This is the binomial expansion. Now, this is something we utilized to construct the interpolating polynomial using forward differences. Now, we are going to use this expansion, 1 minus x to the power of minus n. We are going to use this expansion to proceed further to create interpolating polynomials based on backward difference operators. And you can see that x will be replaced by the backward difference operator, n will be replaced by alpha. When you do that, this is exactly the same as what we are looking for. So this formula, you can derive it, but let's not spend time on that. this is going to look like 1 plus nx, right? So delta alpha, or we can write it as alpha delta. When I say delta here, I mean backward difference operator. It's an inverted delta if you like. So 1 plus alpha inverted delta nx, right? N is alpha, x is inverted delta, which is the backward difference operator. So this term should correspond to this, and then plus n into n plus 1. So alpha into alpha plus 1 by 2 factorial x squared. X is inverted delta squared plus n into n plus 1 into n plus 2 by 3. So alpha into alpha plus 1 into alpha plus 2 by 3 factorial x cube, and x cube will be the backward difference operator to the power of 3, etc. So you can go on forever. And here we have n plus 1 data points. Therefore, we can go till nth order polynomial, because the nth order polynomial will have n plus 1 coefficients. And since we have n plus 1 data points here, we are able to go till that. You should not be surprised that we have this, because e to the power of alpha f of x is equal to f of x plus alpha h. This is something we saw earlier. Now this is what we described in the previous slide, the binomial expansion of 1 minus inverted delta to the power of minus alpha. That is something that is going to give you this. And here we have left it as an infinite series. So this whole operator, which is this, will act on f of x to produce f of x plus alpha h, because this is e to the power of alpha f of x. This is, the right hand side is the equivalent of that, 1 minus inverted delta to the power of minus alpha f of x. So expanding both sides, this side gives you this, the right hand side gives you this long infinite polynomial in alpha. Then we do the usual thing. We will replace x by x naught. So x naught and x naught. Then we are saying we do not want to go for the full f. We are happy with the approximant. The approximant is p of n, a polynomial of order n. So what we do is we stop with this term, because this term would contribute alpha to the power of n. Please note, this is alpha plus 1, this is alpha plus 2, this is alpha plus n minus 1. So you're going from alpha minus 0, if you like, you can write alpha as alpha minus 0. You're going all the way till alpha plus n minus 1. So you're going to have n terms, and the product of these n terms will give you alpha to the power of n. Therefore, this should make sense. So this would be a nth order polynomial in alpha. So that multiplies with f of x naught. And we know that in truncating, we are going to have an error. This polynomial will not be exactly the same as f of x. So there is going to be a residual error, and the residual error is going to be of the order of h to the power of n plus 1, because the leading term that we drop off will have h to the power of n plus 1 in it. So we think of all the terms that we omit in this consideration, the leading term will be the largest, and therefore we say the residual error is of the order of the largest term in the truncated part. All right. One further thing is that the residual will be 0 at the data points in the table, because this is an interpolating polynomial. This polynomial will pass through these points exactly. So the residual will be exactly 0 at those points. It may or may not be 0 elsewhere. So this is how you construct the Newton's backward difference table. We have 5 equally spaced points here. Therefore, the Newton backward difference table will work as much as the Newton's forward difference table will work. When we have unequally spaced points, we will go for the Lagrange polynomial, or we can go for splines, etc. Now, coming back to the Newton's backward difference table, the first two columns are given to us in the form of data. That's what you see here, right? So this is again the data with notation. So you can readily see that the first two columns shown here are going to come from the data table. Then what you do is you start filling out this table. So the backward difference operator applied to f naught will be f naught minus f minus 1. Therefore, from this, I remove this. This difference, f naught minus f minus 1, is going to be this number. So if you look at this delta f naught, when I say delta, it is the backward difference operator. F naught is going to be 216 minus 125, which is equal to 91. Delta f minus 1 will be 125 minus 64, which is going to be 61. This is going to be 37, 64 minus 27, and this is going to be 19, 27 minus 8. So that is how you can compute the first column here. So when you want to compute the second column, which comprises of second order backward differences, delta squared f naught is going to be the backward difference operator applied to delta f naught. And this can be written as the backward difference operator applied to f naught minus f minus 1, which is nothing but backward difference operator applied to f naught minus the backward difference operator applied to f minus 1. That means to get this, I have to subtract this from this. So the backward difference operator f naught minus the backward difference operator f minus 1 will give this value. Again, you can find out the other values, etc. So if you proceed like that, you will come till this situation where you have only one element in one of the columns and there you stop. So this is how the backward difference table can be constructed for any tabulated data. Now, this is the complete table, as you can see. One thing you will notice is the numbers in the columns, the data column included, right? So these numbers for X, these numbers for F are all the same, except that the notation we use is different. Otherwise, it's just the same. Now, if you look at these numbers, you would have seen the same numbers in the Newton forward difference table. So the numbers don't change, except that, again, the symbols we use to describe them changes. All right, so this is one thing that we should understand. And how we use this table is also quite interesting. If we want an interpolating polynomial based on Newton backward difference using x naught is equal to 6 as the reference point, then we would proceed in this direction. If you want an interpolating polynomial using Newton backward differences, and you want it about the point x minus 2, that means about x is equal to 4, then you will go in this direction and pick out these numbers for use. Since the numbers are the same, but the notation is different, if you wanted an interpolating polynomial using x is equal to 4 as the reference point, all you do is start from this but move in this direction, as we did in our example when we constructed the interpolating polynomial using Newton's forward difference table. So the numbers are the same and the direction you go depends whether you want to construct the interpolating polynomial based on Newton forward differences or Newton backward differences. So if it is Newton forward differences, you go in this direction. If it is Newton backward differences, you have to go in this particular direction. That's all. If I wanted to construct a second order polynomial using backward differences, using x minus 2, that is x is equal to 4 as the reference point. So I would say P2 4 plus alpha. 4 is the reference point, alpha is alpha, h is 1 in this particular example. Ideally it should be alpha h, but since h is equal to 1, I would just leave it as alpha. Now we are looking at interpolating polynomials using Newton's backward differences, and we have to go therefore in this particular direction, and we can at the most get a polynomial of order 2, because if you're here and you're looking backward, then only these 3 data points will be involved in the calculation. So if you have 3 data points, because we are looking for backward difference operators, that means you have to look only backwards, the most you can make use of is these 3 data points. And therefore, the highest order interpolating polynomial you can construct is P2, because P2 has 3 parameters. And therefore, we are going for the maximum order interpolating polynomial possible because we decided to use this as the reference point and we also wanted to use backward differences. Therefore, this would be the same as reading off from the table 64 plus 37 alpha plus 18 times alpha into alpha plus 1 by 2 factorial. Remember, we have to use this formula because we have gone for backward differences, and that's what is given here. And we recognize that the error is going to be of the order of h to the power of 3 because n is equal to 2 here, n plus 1 is 3. And we note that this polynomial, as was mentioned, goes through these 3 data points because we are using x minus 2, right? This one, which is got a numerical value of 4. We are using the symbol x minus 2 as the reference point, and we are looking for a interpolating polynomial based on backward differences. So we have to go x minus 2, x minus 3, and x minus 4. This P2 polynomial will pass through those data points. Now, in the two videos, we have demonstrated use of the forward difference table and the backward difference table. You can also use central difference table if that is something of interest to us. And there are not only Newton's polynomials, there are also polynomials that other scientists have put forth. The Stirling central difference polynomial is one, Bessel's central difference polynomial is another. So if you want to use central differences in constructing interpolation polynomials, you can consider these things. We will not cover it in this course. Central differences are more accurate than forward or backward differences for the same amount of computation. Therefore, sometimes that may be a preferred choice. I will stop here and thank you for your time.